now we're going to move on to section 17.3, which is molecular orbital theory. Alright, so if you remember in Organic 1, we looked at atomic orbitals. And from atomic orbitals, we made hybrid orbitals. And so that's where we had an S and 3 P's, and we would make an sp3 orbital, or an S and 2 P's, and make an sp2. With atomic orbitals, the electrons are associated with a given atom. Okay. When we talk about conjugated systems, molecular orbital theory is emphasized. In molecular orbital theory, you're looking at the electrons being distributed throughout the whole molecule. Okay. When you look at molecular orbital theory, you look at the wave nature of electrons. Now, a wave has 2 phases, up and down. So for orbitals, we can represent these phases as shaded and unshaded. So let's just draw a wave. Okay, so these are different phases of a wave, and the idea here is that we'll have this be up, will be shaded, and down will be unshaded. Okay, so if you have an orbital, so let's take a sigma bond. Right. Here, if the orbitals are both shaded, then we'll be in phase, and this will be a bonding orbital. If one is up and one is down, they are out of phase, and this is an antibonding orbital. So this can be represented by sigma, and this sigma star. Each overlap is one molecular orbital. And then we can arrange these orbitals on a potential energy diagram. So here's our potential energy. Now you're going to have your sigma, where the overlap is in phase. Okay, you can consider this constructive interference. And so we have your carbons, molecular orbital. There are 0 nodes. Then we can have our sigma star, which is our antibonding. This is where we had one up and one down, so they were out of phase. This is destructive interference. And if you look at the wave, there'd be one up, one down. You can see there's a node. Now nodes are regions of 0 electron density. And if you remember back to the discussion of orbitals first semester, an orbital is the probability of finding an electron in that defined region of space. So what this means is that when you have constructive interference and you have this bonding orbital, there are no nodes. Here in this antibonding orbital, there is one node. And if we were to fill the molecular orbitals up, we would fill them similar to atomic orbitals, where you would pair them initially in the lowest energy. When we actually have a sigma bond, we have a filled sigma orbital and an empty sigma star orbital. Now, according to molecular orbital theory, the stability of a conjugated diene arises because of an interaction between the pi orbitals of the two double bonds. Okay, so let's look at this a little bit further. Right, first I'm going to just compare ethylene and 1,3-butadiene, and then I'll show you the figure from your text. So if we look at the orbitals of ethylene, and if you remember, ethylene is just CH2 double bonded to CH2. So you can see that the antibonding orbital is higher in energy, We have 2 pi electrons, so this would be pi, and this would be pi star. Now, when we look at 1,3-butadiene, there's a change. So first I'm going to just draw all the p orbitals and their different energy levels. And then I'll explain the picture. Almost done. Okay. We have 4 p orbitals, so we are going to have 4 molecular orbitals. Because we have 4 p orbitals, we have 4 electrons to work with. And again, we're going to fill them so that we fill the lowest energy shell first, and then the second highest energy. Now if you look, the first molecular orbital, let's call this psi 1, psi 2, psi 3 star, psi 4 star. If you look at psi 1, you can see it's actually lower in energy than the pi orbital, the molecular pi orbital of ethylene. And you can also see there are no nodes. You have overlap on the top and complete overlap on the bottom. Now if we come up to the next molecular orbital, psi 2, you can see it's slightly higher in energy, and we have overlap here and here, and here and here, so there's one node. In psi 3, we have 1, 2 nodes, and then overlap of the middle 2. In psi 4, we have 1, 2, 3 nodes. So as the number of nodes increases, the energy of the molecular orbital increases. Now if we look at this molecular orbital here, you can see we actually have a bonding interaction between carbons 2 and 3. Now if you look at the structure of 1,3-butadiene, which I'll just redraw up here, there is no such pi bond between carbon 2 and carbon 3. But as I told you before, when we looked at stability and we looked at bond length, you could see that this structure was both more stable than an isolated alkene, and this bond length was shorter than a normal single bond. So as a result of this, this explains why we see this bond length and the stability of this molecule. It's because of the orbitals being spread over all 4 carbons of the molecule. So if you look here, this is the figure in your text. You have the 4p orbitals of 1,3-butadiene. Here's the first one where it's completely bonding. Everything is delocalized over all 4 carbons. Here's the second one where you have 1 node between carbons 2 and 3. And you have 2 nodes, and finally 3 nodes. So a couple things to remember with molecular orbital theory. Number of atomic orbitals combined equals the number of molecular orbitals. Created. The highest occupied molecular orbital is called the HOMO. This is the highest occupied molecular orbital. The lowest unoccupied molecular orbital is called the LUMO. The HOMO and the LUMO are considered frontier molecular orbitals, or frontier orbitals. The difference in energy is important because we can donate electrons from the HOMO to the unoccupied LUMO. So the LUMO is the acceptor. We will see this interaction in a given molecule and between molecules. So when it's in a given molecule, we're looking to excite the molecule, and when it's between, you're often getting a reaction. So this is going to conclude section 17.3.